Howdy. The point of this video is to talk about how temperature affects electrical resistivity in metals and in semiconductors. Now, just like when we were considering how dopants affect resistivity, it's going to be different in these two cases. So we're going to, again, focus on why. Once again, if we want to think about how something, in this case temperature, affects conductivity or resistivity, we want to think about how it affects the different terms that contribute to conductivity. So N, again, N is the number of free carriers in the system. So how many particles do I have moving around? E is the charge. So if this is just an electron, then we have a single electronic charge. If it's an ion, it could be a multiple of the electronic charge. And mu is the mobility. How easily do these carriers move around? So let's think about how does temperature affect each of these terms differently. First, we're going to think about N. How does temperature affect the number of carriers in a system? So when we drew occupied bands before, we would always occupy them from the lowermost energy up to the point where we ran out of electrons. And we called that highest occupied energy, the Fermi level. Now, this is a nice picture, but it actually is a little bit more complicated than that, because at any given finite temperature, we're exciting some of these electrons up to higher energy levels. And the amount that we excite up is going to be related to the temperature in the system. So if I have something that's exactly at 0 degrees Kelvin, perfect zero, then I will fill up to the Fermi level and stop, and I will have no occupied energy levels above that. Any temperature greater than 0 K, I'm going to have some sort of distribution. And it'll look something like this. So this is a probability distribution of occupation of these different energy levels. So at some energy a little bit below the Fermi level, maybe I have a 95% chance of occupying it. At some energy a little bit above, maybe I have a 5% chance of occupying it. The larger the temperature is, the more smeared out this distribution becomes. So this is called the Fermi-Dirac distribution. And basically it's talking about what are the energy levels that the electrons will actually occupy at some finite temperature. The important thing to remember here is that the higher the temperature is, the more smeared out that occupancy will be. Now in metals, this does not actually matter that much, because we already have a large number of carriers at that Fermi level. So if I increase the temperature a little bit, it's not increasing the number of carriers all that much. That's different from the semiconductor case, because in this case, my Fermi level will be somewhere in here. At 0 Kelvin, I would have no electrons excited up to the conduction band. From the valence band. At any temperature above that, though, I'm going to have some small number of electrons that gets excited up. And the greater the temperature is, the greater the number of free carriers I'm going to have. Now remember, our semiconductors tend to be carrier starved. So increasing that number of free carriers has a very large impact on semiconductors, as opposed to the metal case. So that was N. The charge is temperature independent, so that's not going to change. But next we need to focus on the mobility. Mobility, we need to think about these free carriers moving around. And when they hit some sort of defect, something that's a little bit out of place, they tend to scatter. So an electron does not flow smoothly from a high energy level to a low energy level. It is going to scatter repeatedly, right? So we have this picture of electron path, and the path is actually a bunch of small distances that get traveled before it hits that next scattering site. So as the temperature increases, atoms tend to vibrate more and more. And so I tend to have more scattering events. So as temperature increases, the mobility decreases. It's harder for electrons to move around in the system. this is going to affect both metals and semiconductors. Although remember, semiconductors are number of carriers starved, and it's not as dependent on mobility terms. In the other case, the metals have plenty of carriers. So the metals have plenty of carriers. Their conductivity is more a function of changes in mobility. So what that means is that we have opposite effects in metals and in semiconductors. So in silicon, the conductivity will increase. And that's largely because the number of free carriers increases. Yes, the mobility will decrease a little bit, but not enough to outweigh this increase in number of free carriers. So that's the silicon case. In tungsten, a metal, yes, I will have a few more carriers, but the decrease in mobility is going to be a lot more significant. And so that is going to cause the overall conductivity to decrease in the tungsten case. So both of them have the same trends in number of free carriers and mobility, but because the semiconductors are carrier starved, that impact of the increasing number of carriers is much more important than the impact of the decreasing mobility. In metals, I have that opposite process. Okay, so in summary, resistivity is going to increase in metals as I increase the temperature. The corollary is that conductivity would decrease in metals, right? Semiconductors are the opposite. Resistivity will decrease as I increase the temperature, which also means that the conductivity will increase as I increase the temperature. And just with the role of dopant, just as when we were considering the role of dopants, we need to think about the individual roles of these different terms in the overall conductivity.